How are you doing? So welcome to the Hacking HiSilicon based Cameras for Necessity talk. My name is Ron Munitz. I'm a founder of PSCG Holdings and organizer of the Embedded Israel Meetup Group. You're welcome to join us. I've been doing a lot of satellite launchers, autonomous vehicles, ships, possibly every IoT device you can imagine. I built a couple of companies. I led a pretty strong consulting company. And with this tons of years of experience, I actually dealt with several OTA implementations, which led me to this talk. So what happens is that some very smart software guys, they want to ship hardware devices, but they have no idea what they're doing. They say, okay, let's get some cheap devices. We're going to take 100 devices, maybe 1,000 devices off AliExpress. We'll figure out our stuff, and then we'll move on. And on the other side of the equation, then if you look like at AliExpress, you see a good vendor. They have millions over millions over millions of devices. And a lot of those devices, when you look at competitors, are identical. Like it's the same device, just a little bit for branding. And a lot of other devices, it's the same device. Maybe you add a little bit of more code. But the supply chain is identical, which leads to supply chain opportunity. So the story goes that I had this customer that they wanted to repackage a cheap camera. And they thought that if they buy 30,000 pieces of hardware, then their vendor will do whatever they want, whenever they want. Well, they were wrong, because when they had connectivity issues, then they did not happen like all the time, but sometimes they had no idea what to do, and the vendor did not support them. So I was helping them, and there was an OTA solution that was implemented, and they say, okay, let's try to analyze what's going on, and get a remote shell somehow, and I'll figure it out from there. But the device itself was very limited. 40 megs of RAM, it's very, very, very common. 16 megs of SPI flash, almost nothing writable over there, and an arbitrary size SD card, but you cannot get greedy about it. I mean, you can say, hey, I can do swap space and do everything that, but that's not how it works, okay, on a consumer device. You just don't do that. So they had connectivity issues, and you can either send all the technicians to all the homes, probably not, or RMA everything, which could be okay. So no metrics, no nothing, but an OTA package. Now, I assume not everybody here dealt with hardware, so you have pretty much two options. One, if you want to figure out things, you dismantle the device, get the memory that you need, and then do whatever. The other, if you're lucky, you have terminal access. Our target hardware looked like this. We have this camera. It had some peripherals, and if we zoom into the camera itself, it had an SD card, an HiSilicon CPU, and these exposed pins, if you can see them, they are SPI NOR flash, meaning that you can just take a couple of jumper cables, connect them, and read them. It's very easy. Like a SPI protocol is super simple. However, if you do this like naively, you might power up everything to the device, and then you will not be able to read properly. Now, what happens is that it's a supply chain issue. So different vendors can put slightly different hardware. Maybe you would have SPI protocol, maybe you would have SPI flash, maybe you will have eMMC BG8. You can have a lot of things. Maybe you will have Wi-Fi, maybe we will not have Wi-Fi. So things vary a little bit. And the pros, what they will do, they'll figure out how the device looks like, either by X-raying if they can't see anything, or just by Microsoft in order to do what's called clean lifting. They just want to take off the chip, put it in some adapter, and then read it later. So this is good, and it pretty much works, but you need money, you need equipment, and you need proficiency. Because a good soldierer will do in like 10 minutes, what an okay soldierer will do in 10 hours. And both can break your device. Now, if you have a little bit more of luck, you will have full Linux access, which is terrific. And if it's unconfined, that is, you don't have Linux security modules limiting you and your root, then you'll be able to just disk dump the relevant block devices and either put them on removable media or netcut them. It's all good. So this has no disadvantages. But if things don't work, you need to have UART. You need to see what's going on the boot. So if you have UART, you also have a lot of opportunities. But the most common one would be to do an XDump. That is, it's called MD in U-boot. It's exactly like XDump. Disadvantage is that it might take a lot of time. So my strategy was what most of you would do if you want to dump and don't clean lift the device. It would be getting a serial connection, identifying the OS, identifying the command lines, figuring out what is what, figuring out how to work with the persistent storage, reading it to memory, and then dump it, or get a root shell in Linux and work more nicely. Now what happens is that I was traveling, and I could not get Soldier on plane, at least I didn't check if I could. And I had the following equipment. I had like a 3-port USB with some Ethernet hub. I had an Arduino Uno and tons of jumper cables. And I had a couple of cameras, one that I could break completely, and the other ones could be like the references. So I had this, and I was also provided with some firmware update files to start with, okay? So that was all nice. Assume that I connected all of it and add UART output. Then it would look something like this. You can see 16 megs of NOR flash, and that hit any key to stop auto boot, and then HiSilicon. You do not always have the privilege of stopping boot, but you almost always have the privilege to tamper with the execution by making like some things not being read correctly. So when I looked at the variables, I could see the boot argument. It's uboot, if you know it. Dev mtd block 3 for root, which makes it obvious that if you manage to replace it, you can do whatever you want and just repackage it. Or if you can take over the boot args, that is setenv boot args, dora boot args, and init equals /bin/sh, you get a root shell, okay? So that's nice. The other thing was reading from memory. So at the bottom here in purple, you have this boot m 42 million x, meaning the kernel would boot from there. And a line before that, you have the means to read from the flash, okay? So this one reads 42, it reads about 2 megs from around address 12 megs in the SPI flash. You load it to memory, and then you boot it. And if you can boot it, you can dump it. So with this hex dump, this memory dump looks like this. You just do MD, the address and the count. And what happens here is that you'll get on the right-hand side byte for byte, which is okay. On the left-hand side, for each 16 bytes, you'd get 8 bytes of address, you'd get colon, you'd get spaces, and then for each byte, you get 2 bytes of representations. So that's a lot of overhead, okay? And if you have 16 megabytes of flash, and you multiply this overhead by 8, and divide it by 115,200, then you get over a day in just dumping one firmware. So it's better you know what you're doing, okay? So I actually knew more or less what I'm doing, but if you're naive, if you do something like binwalk, it will get you on an entire flash a lot of garbage, and you need to work really hard to figure out what's going on. And the disadvantage is that you don't really know if your dump went well, and then you need to go over again. This is why the pros always just clean lift. But if you have a Linux access, you can just disk dump, which is what I've done. And then on a target, you netcat, you write on the host, you listen and write to another file. What we have here, the reading from dev mtd, this is the control, this is the character device, but it behaves exactly like the block devices when you read from it. And then you just have all of the partitions. Well, it's very common that the last mtd partition would represent the entire flash. So the partitions were as follows. We had an header, I'll get to it later, uboot binary, uboot environment that in some devices will not necessarily be in the same place, which is important if you want to do something reproducible. Later, an appfs, a squashfs, I'll get to it later. Kernel we already saw, rootfs is rootfs, hardware config doesn't matter, and a writable partition that super matters. Okay, so this was the flash, and I was happy. Now my setup looked like this. I had this Arduino Uno, this nice trick. If you connect twisted to ground, you get a UART to USB adapter. So that's how I could do it like on the airplane, and it was all nice. Then you connect TX and RX to TX and RX in the camera, and this is how the setup looked like, okay? One last thing. The vendor provided a way to do firmware upgrade. You would put a file that looked like this, project name, underscore functionality, underscore app.bin, and then the bootloader that is uboot, it would read this, and if it's legit, just do some things. So in this case, and a lot of other cases, the file name is ipc/app.bin, and if it's legit, it will just boot, and Linux needs to delete it, or somebody needs to delete it manually, otherwise you will continuously update and update and update the software, okay? So that's how it looks. Now let's see how the boot looked at an OTA update, or at a firmware update. So you have here, if you can compare it to the previous slide, you have here MMC reading, okay? It reads this. We have this fantastic file system, the PSCG SD, that's the label. Finding ipc/app.bin, great. Write flash, and then updating offset. So this is an excerpt, but if you look over everything together, you would see that some of the offsets are being skipped, which is awesome because it's an opportunity for persistency across firmware updates. What we also had then, the kernel would boot, and after that, we could see what kernel it is. And here is where things get like nice. because it's 4.9.37. We had millions of vulnerability over all the 4.9 series for many years. It's ARM32, which means if you find something, there is definitely no ASLR. It's not a Google Androidish kernel. And you have like the memory layout, the virtual memory layout of the kernel. And later you have like the dumping of like the MTD partition offsets, but it doesn't matter because you already have it. So the thing here is that if you found something on one device, they have the exact same kernels, like the different vendors just put a kernel object for some additional hardware. You have it for all the possible devices in the root, in the chain, which is good. In addition to it, you have very small memory. It can be 40 megs, it can be 128 megs. But you're definitely destined to have a small distro like BusyBox with microslip-C. So if you have this, since it is a camera, you must also have some video processing tool, right? And you must also have some interface. You have a lot of tools that are, again, used not only in this supply chain, but also by a lot of other vendors. And these tools are super vulnerable. You fuzz the network and you get your way in no time. And they're in millions of devices. So that's a great opportunity. So putting this and adding to it that there is a supply chain, one vendor sells to another vendor and they sell you a product, the original vendor would probably have a way to run very predictable scripts at very predictable time. So if you guess what they are, you can get a complete takeover. So just a little checkpoint. If you have one of these things, kernel user space ports, and you can use Shodan or such a tool just to see what's open, like usually when people do camera research, they say, hey, I did FFplay and saw some feed. But here you want to get takeover. So we're going to use it via like the authentication interface of RTSP or something like that. Then you're done, you win. Now, my objective was not to exploit anything. I wanted to get remote shell on a device on a company I was working with. So we had an OTA file that we could get, and it would be executed somehow. Okay, so I said, okay, I have no observability, I have no tools. Let's get a remote shell and let's get some other tools, like TCP dump, like mmap. I want to have tools. But the problem is that there is very limited memory. So it's not that I could start and putting like a very bloated Python or Node.js things, because they would OOM means that the kernel would kill hungry processes, and it would likely kill processes that will reboot the camera. So this was not good. Also, when you exploit things, you want to have run restoration. I wanted things to work and understand what's going on there. So I needed to craft my things very carefully. And what I did is created, instead of like the payload file, I created an SFX, a self-extractor. And these things work like this. You put a decrypting code first, an extracting code first, and then you chain one after one the files that you want to extract. You know the offset, you know the sizes, and you get one file that is like this company binary over there. So the self-extracting looks like this. You'd have offset, this XXX, YYY, ZZZ over here. And you know them, so you jump to them and then extract them via DD. So you go DD, skip offset, extract size, skip offset, extract size. If you have executables, you change mode to them, you make them executables, and later you can run whatever you want, like installing BusyBox of your choice, and like putting any shell script that you want of your choice. And if you get this running early enough, then you can win. You can do whatever you want, and then that. Now, self-extracting also need to have the offsets, and this is very easy to calculate. You just go ahead, DU the files that you want, and set the XXXYY on the other slide. So making the extractor is like the decrypting code. The extracting code is this green one. You just chain them one after the other, after the other, after the other, and then you have a super legit file, executable file that you will run as your self-extracting, which is good, because if you have this, you can do CNC, you can get more instructions, you can run more things, and you can run a remote shell, which is what we've done. On the right-hand side is the CNC. It just listens with a Python HTTP module and serves some files, some commands. And you open from the terminal, you open a reverse shell, you just open a netcat. And on the other side, the nice thing about BusyBox netcat is if you do netcat-e.sh, you're done. You got yourself a remote shell. So I had this, and I figured out a lot of things that I needed. But it's because I had an entry point that I knew of. What you would do if you wanted to research something like this, you'd look at the firmware and try to see where are the commonalities. And in this case, they were very easy. Upon boot, it would mount a squash FS that was called appfs. I told you I'd mention it later. which would look for a bashrc.sh file, not .bashrc, I mean, this is how they called it. Later, it would mount a writable partition, and if it had a file called etc confd startup.sh, it would execute it and then exit. So it's obvious that if you override this, you win. Okay? Otherwise, it will run a startup.sh that is in another read-only partition, and the exploitation is pretty obvious here. Okay? So by this point, I was done with the original task. The vendor got its logs because I did my stuff. I redirected the output of all the binaries that they read, gave them their outputs, redirected proc kmessage, the kernel log. We had everything, they troubleshooted stuff, and everybody was happy. But they were slow and did not provide the image. So I said, okay, no problem. Let's replace the image. Now, the naive researcher can think that if we have a squashfs and we can DD it in, we can DD it out. But it doesn't really work this way, because if you do that and write to a block device that it's in use, you're very likely to corrupt the flash. So this is not good. So I said, okay, there is an OTA mechanism, there is a way to flash firmware, let's package it ourselves. So that's what I've done. So I started to look at it, and I had a flash dump. Now the flash dump, it looked exactly like the reference firmware burning implementation, only that the firmware burning implementation had a little bit, a small header. So it was good because those headers usually are trivial. So it had like some lens, some strings, and it had a checksum, and I figured out everything except for the checksum. So what did I do? I dumped uboot. Here we have an example of the end of the uboot binary. It has some strings and the beginning of the environment. I separated the environment, reverse engineer uboot. Of course, I figured out that the checksum was just summing all the bytes in the file. I could have just guessed that, but I didn't. I found out that there are options to just replace some of the partitions, like kernel, appfs, and so on. And while doing that, I already started looking at other devices, like just for fun. And then I saw that sometimes you could not update the flash at all. Sometimes the environment were in other places. Sometimes you needed to actually glitch your memory to stop at uboot. But then I started like doing the real research while working on it for fun. So of course, after we figured out the problems and I figured out how to package it, they got me the code to pack the software after working so hard. But I mean, it worked and everything was fine. Back then also somebody told me about OpenIPC, that if any of you is interested in these security cameras, you should know this project. It could have probably saved me a lot of time, but I never really looked at it, so I don't know. So to conclude all of that, what we've done, we took a camera, we tore it open, we enumerated it, we found that it had an old kernel version, we had tons of vulnerabilities for it, and we actually saw how the startup sequence worked. We went and we understood how to replace everything in the file, in every partition in the device. We had complete takeover of the device. We can do anything that I wanted, I could do it. I say we, but this was like a one-person job. It was just a byproduct. And on the way, we found like super trivial vulnerability in some camera daemons that are literally everywhere. And if I were you and I were looking at it, I would just start with the easy things. I mean, I come from a kernel background, so I just saw everything. It was obvious for me there are tons of vulnerability. But if I had to start it and I was not coming from this background, I'd just start with the daemons and I would figure everything out. It was really easy. But the really important takeaway is that there are millions over millions of devices there, and you could just get them with Showdown. So it was pretty nice. This was not the intention. All this research is like a byproduct, a nice byproduct. So the end of the story goes like this. I managed to find a problem. Awesome. That company kept spending a lot of money and doing really stupid things. Great. At some point I say, hey, if you want me to stay, we're starting a hardware division and we're doing it right. And with independent budget. And they say, no, thank you. And I say, I'm leaving. And they say, bon voyage. And I say, merci beaucoup. A couple of years later, after they spent like $30 or million, they got a lot of employees, they shut down their businesses. So all this hard work to repackage it and find things, for what? So it got us to this talk. So I hope it was worth your time. And thank you.